Now, we talked about this idea that another thing is not just that we want to make claims about causal stuff, which has to do with what we call internal validity, but we also want to know whether or not this stuff generalizes to the larger group, the population. And this gets us to a distinction between doing a census versus what we call sampling. A census is where you measure all units in a population. And as we said, this is almost always impossible. So what do is we sample, which means that we get a subset of cases from our population. And this subset of cases from our population serves as our sample. So sampling can be done in many ways, and how you sample is another thing that's critically important to think about the strength of claims you can make. Now, in a somewhat different way. When you're talking about this X cause Y, it has to do with how the internal design of the study is, right? When you're talking about this issue, you're talking about, does whatever you found in a single study apply more broadly, right? So sometimes you care about one more than the other, depends on what you're studying. So there's this inevitable principle in statistics that sampling error will exist. And sampling error is not error as in, oh, you made a mistake. Sampling error is an inevitable discrepancy. So it is a discrepancy between a statistic and a parameter that's due to sampling. Now, sampling error can be bigger or larger depending on practices, at least probabilistically speaking, it can be bigger or larger. So how I sample, if I sample real poorly, I might have a much larger sampling error, a greater discrepancy between my sample and the true population value, right? Which again is a parameter, right? Statistic describes a sample, parameter describes a population. So if I'm trying to take a statistic and say it's going to stand in for the unknown parameter, I want to know that my sampling has been done well. Now, if I sample poorly, that statistic might not do a good job at all of representing my population. If I sample well, then hopefully that discrepancy will be minimized. But there's no way to ensure, in fact, it's essentially impossible that your sample value will be precisely the parameter value, right? Because there's an infinite number of values for things that are continuous in and of themselves. So like the chance that you would fall on that exact number in an infinite range is by definition 0, because divide by infinity, right? So like it wouldn't happen. So like there's going to be some deviation. But the whole point is that it can be bigger or smaller as a function of how you sample. So it's super critical. But there will be differences, and that doesn't mean you made a mistake. That just means that because you happen to have a sample, it's not going to be the full population value. But that doesn't mean it doesn't represent it well, right? So this is the idea of having a sample that is representative and an estimate that is unbiased, right? So we can have great confidence, and that's why, like we said, when we get into inferential, it's always with degrees of confidence. There's always margin of error. We don't think that our number is the number, but rather we can say, well, here's the number we got, and based on the confidence we can have based on our procedures, here's the margin of error, right? So that's critical. So probabilistic sampling is the preferred way to do this, and this uses probability, chance, random processes, because again, chaos, it's fair, right? So random is fair. So probabilistic sampling, like all of them essentially involve something random. Simple random, stratified random, cluster random. Systematic is kind of like a pseudo-random is what but we won't go into like great detail of trying to describe all of these, as this is not a methods course, and this won't be like super critical. What is critical to understand in this class, because it will come back, is the idea of a simple random sample. A simple random sample is where each and every unit of analysis has an equal and constant chance of being selected. So, if you needed to get a random sample of people in the class, what could you do? Well, some people say, oh, well, let's put everyone's name in a hat and pull one out. And I say, well, that could work, but it only works if you put the name back every time you pull one out. Because otherwise, the chance of being selected changes, right? So there's 1 in 35, 1 in 34. So an easy way is, for example, to assign everyone a random number and then use a random number generator to select numbers. So if I want to get 10 of my 35 students selected at random, if I give everyone a number and then randomly select 10 numbers, that is a simple random sample. Every student had a chance of being selected, right? And an equal and constant chance, okay? So simple random samples are important, and we'll come back a little bit in some of our probability stuff. But the important big picture thing here, probability sampling uses randomness to allow everyone in a population to have a chance and an equal chance in some way of being selected. And so it removes bias, right? And it allows for greater representativeness. That is, the sample is more likely to represent the population. And I think this is really important to understand because a lot of students mistakenly assume that when it comes to sampling, I just need to get a really big one, right? But I always say when it comes to sampling, it's not the size, it's how you do it, right? So this is totally true. You could have an enormous sample that is not at all representative. And you could have what seems like kind of a small sample that was representative and actually does a good job of describing your population. Going back to the idea of voting patterns, that's a great example. If we truly randomly select 5,000 Americans from the American voter registries, right, and ask them how they're going to vote, those 5,000 people will serve as a fairly good estimate for America's patterns of voting. However, if we got 1 million people, but we selected them all from the same area in Texas because it was around us, that's not going to do a good job of representing Americans' voting patterns, right? Because what you did is a convenience sample. It's non-probabilistic. And so you selected everyone based on some shared characteristic or similarity where they were in Texas. So even though you have a bunch of them, it's going to be a biased estimate. And so this is why it's very important that the way we sample is critical. Unfortunately, it can be really hard to get random samples, right? You can imagine if I'm trying to study depression, how do I randomly select people with depression, right? And there's a bunch of practical constraints. In methods course, you'll deal with some of that stuff more. We won't go into all that, but here it's important to think about when we're talking about generalizing statistical findings, talking about how well they stand in for these populations, because the whole point of inferential statistics is to have a sample essentially stand in for a population, to be able to make an inference about a population from a sample, right? So how you sample then is critical. So that other way is non-probabilistic sampling. Non-probabilistic sampling is where you just get people in some way that is not based on randomness. Convenient sampling is where you use units of analysis that are simply easy to access. Because they're nearby, they're easy to access and measure, there you go. Now this doesn't work well for representativeness, right? If I just measure all the students in my class, the chances that you guys represent all the people at GCC, probably not. There could be differences in people who take online stats or not. There could be differences in people who are psych majors or non-psych majors, right? And so like you guys are a particular set that doesn't represent the population as a whole. You just happen to be easy to measure if I wanted to, right? Purposive sampling. Now this is often used in qualitative research, but in quantitative research that uses statistics, it's not as good an idea. This is where you pre-select people based on some predetermined criteria, right? Like I want someone like this, okay? Quota sampling is where you try to build a sample by design that reflects some numerical composition of a population that you're interested in. So for example, if I know based on census data, the breakdown of ethnicity in the United States or race in the United States, and I decide I want to get the same proportions in my study. So I get the right percentage of white, the right percentage of black, the right percentage of Asian, you know, and so on to match America's composition. Well, now I know that the composition of my sample matches the composition of America's distribution of race and ethnicity, but I haven't selected them at random, so they may not generalize well because of all the other things that I didn't think about when I was selecting them just based on race and ethnicity. Another example is snowball sampling, and this is where you basically refer a friend, right? So like I get someone to be part of my study and be like, hey, tell your friends about my study, and then like their friends come and I measure them too. Obvious problem here is friends are more similar than non-friends, right? And so like when you do this, you're likely to have a biased sample that is not representative. So these are all a bunch of issues when we talk about trying to do statistics and trying to go from a sample to a population in inferential statistics.